Mr. John here. Welcome to my video today about ZIML Division H. The Zoom International Math League Division H is all about exposing people to high school mathematics. I want to do some sample questions with you guys today and explain a little bit how this is a great bridge for those of you wanting to switch from AMC 8 to some higher level math competitions like AMC 10, 12, or also to practice some of your high school math if you're already in high school and apply it to problems. Quick summary of this division, right? Typical math standards: Algebra 1, Geometry, Algebra 2, Pre-Calc, right? Integrated Math Series 1, 2, 3, those kind of all work as well. You can always check out our video, we'll link it down below, with a full summary of this division and all the other divisions as far as the monthly contests are concerned. But really the best way today to show you what Division H is all about is by doing some problems with you. So why don't we just jump in, we'll solve some of these problems together, and that'll give you an idea what this division is all about. So, first question here is a little bit of a mix of algebra and geometry when we start thinking about the question. So we have three lines: y equals 2x, y equals x over 4 plus 5, and y equals 0. These three lines form the boundary of a triangle, and we want to find the area of that triangle. So first of all, we want to at least get a rough idea what our triangle and therefore what our lines are going to look like. We don't need a perfect picture, but right, we know y equals 2x is a line with slope 2. This goes through the origin at 0, 0. If we look at our next line, y equals x over 4 plus 5, right, that line has a slope of 1/4. It has a y-intercept of 5. So that's going to look something like this here, right? Graph might not be to scale, of course, things like that. But we want to focus mostly on the rough idea of what we can be thinking about in terms of our triangle. So then our last line, of course, is y equals 0. And now we're starting to see how the algebra and the geometry are related, right? We have a base of our triangle kind of on the bottom. We can then use information about where these lines intersect to find the height as well, right? So kind of if we start labeling those things, right, pretty clearly this is our base at the bottom. And then remember, for the height is always going to be perpendicular to that base. So if we drop this perpendicular down right here, that's going to give us our height of the triangle in this problem as well. So now we can kind of have that rough idea of the geometry. We need to go back to the algebra to start figuring these things out. Right, we kind of have 3 points, if we like, here. We have a point A, that's the origin. That one's pretty easily 0, 0. We have our capital B, and we have our capital C right here. So for the base, right, if we do this one step at a time, for our base, right, we need A and B. So pretty clearly A, right, is the point 0, 0. Of course, this is the intersection of y equals 2x with y equals 0, so that's just at 0, 0. How do we find B, right? B is the intersection of y equals x over 4 plus 5 and y equals 0, right? So now we have our blue line and still our green line. So when y equals 0, we have x over 4 plus 5 is 0, right? So we can solve for b is -20, 0 as well. So that's what we have for our point B. Now, what does that tell us about our base, right? What is the base of our triangle? This implies the base B is equal to 20, right? We have a 0, 0 to negative 20, 0. That's pretty clearly a length 20 in that case. So for the height, we're just going to actually need C. Height, we need C, right? And so C is the intersection of the red and the blue. So y equals 2x and y equals x over 4 plus 5. So again, this is where the algebra comes into play, right? We have two equations. They're solved y equals, so maybe it's easiest to find x, and then we can use that to find y. We'll kind of go towards another system of equations towards the end of this video with one of our later problems. But for here, we have 2x equals x over 4 plus 5. So if you solve this, right, you're going to get 8/4 x. 2x is 8 over 4x minus a fourth, so that's 7x over 4 equals 5. Multiply by the reciprocals on both sides, x equals 20 over 7. So this tells us then that y is 2x, right, equals the height, right, equals 40 over 7. That gives us our height of the triangle then, right? So we're just kind of taking this piece by piece. Area of a triangle is 1/2 base times height. We've now found the base using algebra. We found the height using algebra. And so now we're ready to put everything together to give us our final answer, right? So the area of our triangle equals, right? And let me kind of put this in a color to stand out here. Area is 1/2 times the base times the height. So this is equal to, right, 1/2 times 20 times 40 over 7. So this is 400 over 7 as our final area. So that's going to be giving us our answer for the problem here. Now, I want to use this opportunity just to quickly say again, right? Be sure you're reading a question carefully in terms of what you want the answer to be. If this was an actual ZIML Division H problem, we would maybe have you do a decimal approximation. So you'd want to be sure you know what we're asking for. Maybe we ask for the numerator plus the denominator in the simplified fraction, right? But depending on the context, right, depending on where you're taking it, whether it's a multiple choice test or a short answer, right, numerical answer test, you want to keep all of those things in mind when you're coming up with your final answer and kind of explaining that final answer as well. Okay, so this was a good mix, right? We had some algebra, we had some geometry for solving this problem. Let's take a look at our next one. So our next problem here is a number theory. We won't spend too much time on this one. This one's a little bit easier. But let's read it first. There is one 2-digit number that is equal to the square of the sum of its digits. What is this number? So, 2-digit numbers and square. So if we just think about that original line, or this top line here, 2-digit number that is equal to the square of blah, blah, blah. Even ignoring what the restriction is here, there's not too many numbers that are perfect squares that have 2 digits, right? So this is kind of a good way to get started with narrowing down the options, right? Even if you don't know how to immediately solve a problem, you can at least narrow down, start making some progress, and oftentimes that'll help you with a flash of insight. Oh, now I know how to solve the problem. And in some cases like this one, you'll say, oh, it's actually pretty easy as well. So we can start with the question, what are the 2-digit squares? So which numbers that have 2 digits are perfect squares as well? So you could just start listing these out, right? We have 16, then we have 25, then 36, then 49, then 64, then 81. And just to remind ourselves, right, where are these coming from? This is 4 squared, right? 5 squared, 6 squared, 7 squared, 8 squared, and 9 squared. So we'll kind of keep that in mind when we're thinking about this as far as the next portion of this problem is concerned, right? We can start listing out here all of these perfect squares that have 2 digits in this case. Now, we go back to the full wording of the question, right? This square is supposed to be some specific square, right? This is the square of the sum of its digits. Well, we have 2-digit numbers. It's pretty easy to find the sum of the digits in that case. So now I won't do all of these, but to start seeing them here, right? 16, that's 4 squared. That is not equal to 7 squared, right? Where is my 7 coming from? 1 plus 6. 5 squared is definitely also not equal to 7 squared. 6 squared is not equal to 9 squared. But now, wait a second. Have we seen a 9 squared before? Yes, we have. 81 is 9 squared. And wait a second. 9 squared is equal to 9 squared, which is equal to 8 plus 1 squared. So in fact, just by trying some of these, just by reading the problem kind of carefully, we can figure out, okay, what is our missing number, right? This number has to be 81. This is our mystery number in this case. So we just kind of do it piece by piece there, right? So for some of these scenarios or, problems you might not be so accustomed to, right? You don't do as many number theory questions in school, but you just want to take them piece by piece, and you'll realize a lot of the times they're actually pretty easy once you kind of take them piece by piece like that along the way. Okay. So that's a good number theory example. Let's continue on to our next question. Here we have a pure geometry question, which is going to test some of our vocabulary and things like that as well. So a square ABGH is drawn sharing one side of regular hexagon ABCDEF as shown in this diagram below. So first of all, some vocabulary, right? What is a square, right? Of course, we know a square has all equal sides and all equal angles, and all of those angles are right angles, right? So square, right, 4 equal sides, 4 right angles, right? 90 degrees each. And what about regular hexagon, right? So we should be all 100% comfortable with squares. We maybe aren't as used to hexagons, but anytime we have regular, that means equal sides. And all the angles are equal as well. So here we have 6 120-degree angles. Now, if you want a quick refresher about that, where do these 120-degree angles come from? Remember, you have a formula for this. So 120 here is 180 times 6 minus 2. So you take the number of sides minus 2, and then you divide that by the number of sides. So actually, all 6 angles add up to 180 times 4. That's 720. So all 6 angles in that hexagon add up to 720. So each of them individually must be 120. Notice this formula works for a square as well. 180 times 4 minus 2 over 4 does give us 90 degrees each there as well. Now, if we focus first, however, on these equal sides, well, all the sides of the hexagon are equal. So if DE is 3, so are all the other sides of the hexagon. So we have 6 sides all equal to 3. Well, wait a second. A square has equal sides as well. So all of the sides of the square are also equal to 3. drawing in those right angles as well, right, we definitely know kind of everything we need to know about that square. So the square ABGH definitely has an area of 9, right? We can kind of keep that in mind immediately there as well. Now, combining our angle stuff too. So let me highlight here, right? We have 120-degree angles in our hexagon. Well, wait a second. We have a 120-degree angle then here. So what is this missing portion of the angle, right? So what if we want to find angle CBG? So we're looking at that single angle CBG there. Well, that's the whole angle. That should be 120 minus our right angle. So we have minus 90 degrees. So this angle is 30. So we can actually figure out now that both of our triangles, right? So both of these are equal to the same angle. Both angles here are going to be 30 degrees in this case. So using our angles to kind of summarize that, right? So using our angles, right? Angle CBG equals angle HAF equals 30 degrees. So now we kind of have all of the information we need about our square and our two triangles as well. So now let's start putting it together. Now, you probably all know 1/2 base times height. We already used that for the triangle, right? What about our different formulas for the areas? So the square has an area of 3 times 3 equals 9. So each triangle, right, is an isosceles triangle with side lengths 3 and an angle of 30 degrees. So remember, we have a formula using side lengths and the angle. Has area 1/2 times the two sides, so times 3 times sine. So this is our first kind of exposure to some trig today. So we have 1/2 times 9 times sine of 30, which is also 1/2. So in fact, each of these triangles themselves has an area of 9/4. So 1/2 side, and the angle in between them. Now we're ready to put everything together, of course. So area of the hexagon is all of these areas added together. 9/4 plus 9 plus 9/4. This is the same as 9 plus 9/2, which is 27 halves equals 13.5. Right, so this is the area of the shaded hexagon, our kind of hexagon ABC, GHF, to be clear as well. So that's what we have for our final answer in this case. So again, it's just breaking down the problem piece by piece there. So you read the question, what do you know? Oh, I know about squares. Wait, I also know about regular hexagons. Oh wait, that also tells me what the two triangles on the side, right? We have two congruent isosceles triangles, and we can find their area pretty easy in that case as well. So that's kind of perfect there too. Moving on then. Here we have an example of combinatorics. So combinatorics, remember, is some statistics, some probability, maybe some counting as well. Here we kind of have a statistics / probability question. As part of her AP Stats project, Carrie polled freshmen, seniors, and teachers, so the 3 categories in our columns there, and asked which sport they preferred between baseball, basketball, and football. Our 3 rows, freshmen, senior, teachers, columns, baseball, basketball, football. Of course, being a math question, we're only giving you partial data here. Probability that one of the people Carrie polled who preferred baseball was a teacher is P%. So what is P here? Now, There are some quicker ways of doing this. So I don't want to say the way I'm going to tell you how to do this is the most efficient, but I just want to practice here in a sense of filling in everything first, right? If you kind of pick and choose and work carefully, you can kind of say, okay, what's the exact data I need to solve the question, and kind of go from that data only. But here, I'd rather kind of just look at filling in the whole chart. So let's fill in our whole chart, find all of our missing data, right? Fill in all of these totals and work from there as well. So when we're thinking about this, however, we're just kind of using information one thing at a time. So the total number of people here, we actually have, right, anytime there's a row or column with one missing, we should be able to fill in that. In total, 18 like basketball, or sorry, 18 like baseball, 35 like basketball, 27 like football. So, hey, that means that there are 80 people in total. And we can start filling in all the missing information this way. Basketball needs to add up to 35. So 18 and 7 is 25. We're missing 10, right? Same thing for football, right? We have then 15 and 3. So that's 18. We're missing 9. So we have 9 people who must like football in this case. So you just can be thinking about all of your missing information and start filling that in here, right? So now, how many people are freshmen? 3, 18, 9. We have actually 30 freshmen there, right? Seniors, 10 and 15 gives 25, so there's missing a 5 for the baseball, meaning there have to be 10 teachers here. And then luckily, this adds up to 20 for the total number of teachers as well. Why do I say luckily? Well, the total on the 30 plus 30 plus 20 had better equal the total on the 18 plus 35 plus 27, or if something went very wrong with our arithmetic along the way. So once you have this full chart filled in, like I said, we could have picked and choose to find out exactly the information we needed to solve the problem, but once we have the whole chart, basically any question we ask you guys now is easy. We just have to read carefully, okay, what do they want? What numbers are relevant for that? So we're doing probability, and in particular, we're doing probability of the people who preferred baseball. So we filled in the whole chart, but now, okay, who likes baseball? We can narrow in just on this first column right here. There are 3 freshmen, 5 seniors, and 10 teachers for a total of 18 people who prefer baseball to the other sports. Now, of all of those, right, the probability that one of those people who preferred baseball was a teacher is p%. So now we want to say, okay, how many of those people were teachers? And this is what we're combining for our probability. So, right, there are 18 people in total who prefer baseball. Of them, 10 are teachers. So this gives us a probability is 10 over 18 is 5 over 9 is approximately here 55.56%. So that's kind of giving us our approximate answer in terms of P. The official exact probability is 5/9, but then deciding how we want to present that, here they're telling us we want to present that as a percent. So about 56% of the people who preferred baseballs were teachers. Okay, so that's a good example here in terms of talking about our counting and probability, right? Talking about, okay, we're doing a chart, let's fill in our missing information. Once we have that missing information, we can start thinking about exactly how to use that information to solve the question at hand. Okay. As I promised earlier, right, our next problem here is really focused on a system of equations. So we're used to seeing system of equations, right? Probably most of you have done systems of linear equations, right? Maybe you even have 3 variables, right? 3 linear equations. Here we have some things that are a little bit different. Our first equation has an absolute value in it. Absolute value of 2x minus 1 minus y equals 2. Second equation has a square in it. X squared minus y equals 1. So we have this idea of a system of equations. We also have ideas of absolute values, of squares, but we're combining them all into one problem here. For a lot of these system of equations, or even system of equations that you don't think of as system of equations, what do I mean by that? I mean, you're also used to probably solving for intersections of graphs, right? We have y equals 2x plus 3. You have the graph y equals 3x squared. Where do they intersect? So maybe a good place to start here is just rewriting these in terms of graphs. What is y equal to? So in our first expression, if we add y, subtract 2 on both sides, we can actually get that y is equal to the absolute value of 2x minus 1. And then we have minus 2 in that case. And in our second case here, we're going to have, right, again, add y, subtract 1. We have y equals x squared minus 1 here. So now we have transformed this expression, this system of equations, into like a y equals in both cases. So in other words here, right, of course we want y at the end, right, because y is our point of the question, right? What is the largest y? But we can look at the equation here, right? Setting these equal, x squared minus 1 needs to equal the absolute value of 2x minus 1 minus 2. So maybe even let's clean that up a little bit, right? Once we have it written in this format, right, we can, okay, add 2 on both sides. So this will maybe be a little bit nicer to look at. We can say kind of x squared plus 1 needs to be equal to the absolute value of 2x minus 1. And now for the rest of the problem, this is going to be kind of our focus of solving. We have a squared on one side and our absolute value on the other. We've kind of dealt with the system of equations part here, right? This is now one equation, right? This will allow us to solve for x, and then kind of once we solve for x, we're going to be in good shape for finding y as well. Now, remember how we deal with absolute values, right? So let's put this off to the side kind of too, right? For absolute value of 2x minus 1, what are some things that could happen? Well, anytime an absolute value is positive, we do nothing with it. It just stays the same. So where is 2x minus 1 positive? If x is greater than or equal to a half, then absolute value of 2x minus 1 just becomes 2x minus 1, right? If you plug in like 1, 2x minus 1 when x equals 1 is 1. So that stays the same, right? 2, 3, all of those values there, it just becomes 2x minus 1. What happens if an absolute value is negative? Well, you have to make it positive, right? So if x is less than 1/2, 2x minus 1 is negative 2x plus 1, right? Remember, that's just saying you flip the sign of your expression. If we try to plug in 0, we get 2x minus 1 is negative 1, but then absolute value of that is 1. Notice that's the same as plugging in 0 to negative 2x plus 1, right? So that's exactly what we're doing here. But then this is kind of giving us two cases to deal with, right? We have two separate equations that we can kind of solve in this case. So if x is greater than or equal to a half, right, what does that tell us about our expression here? Well, we have x squared plus 1, and what is that equal to? That is just equal to 2x minus 1, right? So everything is positive in this case. So everything positive for our absolute value there. So x squared plus 1 equals 2x minus 1. So quadratic equation, x squared minus 2x, and then we have, right, plus 2 equals 0. Now, there's lots of ways to solve a quadratic equation, right? One of them, if factoring fails especially, is the quadratic formula. And in particular, you oftentimes want to think about what's inside the square root, right? Inside the square root, this is referred to as the discriminant. And the discriminant is helpful because it tells us when we have real solutions or not. So if we looked at inside the square root, we would get negative 2 squared. Maybe let me write this down. I'll erase this in a second. But we have negative 2 squared minus 2 times 4. So this is 4 minus 8, so this is negative 4. So what is this really telling us here? Whoops, this is really telling us that we have no real roots. So this case actually leads to nothing. So this has no solutions here. No real solutions. Of course, sometimes, and even in Division H problems, you might deal with, complex numbers, complex roots, things like that. But this is not one of those scenarios. There's no real solutions in this case. Okay, so at least if the problem's going to make sense, something better must happen in our second case, right? So here we can look then at this second case as well. So in this one, we have x squared plus 1 equals negative 2x plus 1. And so once we cancel the 1's, we have x squared plus 2x equals 0, x times x plus 2 equals 0. So this gives us values that work, right? So one of these values is x equals 0. And the other value is, whoops, not y yet. We'll get to y in 1 second. The other value is x equals negative 2. So we have two solutions for x. Of course, we want to find solutions for y as well. So if x is 0, what is y? Y then is going to be negative 1. 0 minus 1 is negative 1. If x equals negative 2, we have 4 minus 1. Y is going to be equal to 3. So those kind of are the two sets of solutions we have here. Going back to the question, right? Remember, we always want to figure out what is the question asking. Here, the question is asking us for the largest y in this case. So the largest y is going to be 3, right? We have our final answer is just y equals 3. That is the largest y for the problem here. That is good, right? System of equations, some algebra stuff there as well. Let's have time for one final question here before some wrap up as well. And I want to do one more of these trigonometry questions here. So we want to simplify the expression sine squared of 30, sine squared of, or cosine squared of 80, sine squared 30, sine squared 80, cosine squared 45, etc., etc., etc. Let's kind of come back to that expression in a second here. So for any of these things, a good thing to think about as you're getting started is, do we see some similarities here? So in fact, this whole thing is made up of sine squared of 30 times some stuff. Then we have some pieces here where we have cosine squared 80, sine squared 80. So we have some pieces with the 80-degree angles. And we also finally have some pieces with 45-degree angles as well. Now, let's do a quick review of these kind of 45-degree angles to start. So you could calculate these, right? So cosine of 45 degrees is square root 2 over 2. So cosine squared of 45 degrees, right? If we wanted to actually kind of calculate this out, we have that this is equal to square root 2 over 2 squared is 1/2. Similarly, actually sine of 45 is exactly the same. Now, you might have recognized this right away, and if you did, good job. But also here, this should hopefully jog our memories. And of course, I mean sine squared here the second time. This is telling us that cosine squared of 45 plus sine squared of 45 is 1. Now, is anything special about the 45-degree angle in that case? Actually, no, right? So remember, this holds in general. Remember, no matter what angle you have, right? Let me put this here. This is one of your most important, the most important trigonometric identities, right? For any angle x, right? Sine squared of x plus cosine squared of x equals 1. This is our analog of the Pythagorean theorem, right? That's all it kind of is in this case. So now if we kind of do this piece by piece, we start to see some stuff coming together pretty nicely here. So let me kind of change my highlightings a bit to kind of see where we can go from here. Well, if we look at our last two lines, so let's just consider the last two lines of this expression right now. So if we look at the last two of those lines, notice that the last two of these lines becomes what? Well, what do we have in common? Do they share anything here? So the last two lines are, well, they both have a sine squared of 30. They both have a sine squared of 80. And then what's left? What's left is actually exactly our 1, right? So this is all times cosine squared of 45 plus sine squared of 45. So this whole thing is just sine squared 30 times sine squared of 80. But now what happens when we combine that with the first line? So if we bring in that first line as well, so bringing that first line all around down here too, notice that has a cosine squared of 80. So with the first line, we have, okay, the sine squared of 30 comes out. We can pull that out. And now we have cosine squared of 80 plus sine squared of 80. Can we calculate without a calculator cosine of 80, sine of 80? No. Do we care? Also no, because this then just becomes sine squared of 30. Well, sine squared of 30 is 1/2, so this whole thing just becomes 1/4 after we simplify. So simplifying it, actually most of the things cancel out, right? All of our kind of messiness comes out of this. We can actually write it just as a number 1/4. So that's what we get here as our final answer here. that brings us to the end of our kind of practice problems. Really quickly at the end here, right, remember all of these problems have come from previous ZIML Division H monthly contests. So I really hope, especially if you enjoyed some of these problems, want to see more of them, visit ziml.areteam.org, right? You can see kind of all free problems there, free daily practice problems. We have sample monthly contests there. There's all kinds of great contest resources if you're doing AIMC 8 or other AIMC 10, 12 contests that way. And if you want a book, right, you want to say, okay, I want to do some of these problems. We have all the solutions there as well. You can check out our bookstore, and we have all kinds of old ZIML books there too. Now, you might also ask, right, what if I want a more systematic approach? So Math Challenge 1C is one of our kind of year-round classes. We have this as year-round classes, self-paced classes, intensive classes sometimes. This really provides you the kind of highlights of Algebra 1 and 2, geometry, beginning pre-calculus. We oftentimes use some of these Division H problems as supplements in this course. But this covers a lot of those knowledge points in algebra, right? And some more advanced algebra, geometry, finite math, which is your sequences and series, some number theory, some counting, some probability. All of those most important topics if you're transitioning into kind of AIMC 10-12 prep, into ACT, SAT prep, this course is going to give you a great foundation to kind of see all of those things along the way. But for now then, right, I'll leave you with the ZIML slide again, but Mr. John signing off for today. Thank you guys all for solving some of these problems with me, and I hope to see you guys all again soon. Goodbye.